So far we have discussed three main items regarding the applications part of this course. One is the introduction to electronics cooling. We discuss some aspects of what needs to be looked into for design of these thermal solutions. Then we looked at what is the right heat transfer coefficient, where we discussed primarily emphasized on the adiabatic heat transfer coefficient. Then in the then we talked about how to assess when one goes about enhancing heat transfer, how to go about assessing whether the structure is going to fetch you a positive result of either enhancing heat transfer or reducing pumping power, or it is going to give you some kind of compactness in terms of size. So, we discussed that all these aspects, and here we go into some depth on heat sinks where convective heat sinks are being designed, and the goal here is to keep it at a level that we can use some of the results that that was discussed, but towards more towards practical aspects. So, again, even though this is meant to be meant or discussed as part of electronics cooling, but all the work, all the discussions hold true for any place where a heat sink or a heat exchanger or some kind of thermal cooling solution needs to be implemented. So, moving on. So, there are multiple configurations that are often involved when we talk about heat sinks. One is the flow enters through the side and exits on the through the side. It is called side inlet, side out exit. Then you have jet impingement, where a jet of air impinges on normal or in at an angle. Typically, for example, a fan is mounted on top of a heat sink. We will look at one of the examples in the upcoming slides. You can have flow modulations, geometric modulations, modifications, and so on. So, we will discuss some of these things. First, we will talk in the part 1 of this, the heat sink solution itself, and then we will discuss some of the later results. You may recall from the previous discussions, there is the wedge solution that was discussed as part of this course, and we can use the wedge solution to understand this was the solution and it had a wedge angle. Now, I am using beta pi as a wedge angle, but so here if I had a wedge angle and if I wanted to say my angle is 90 degrees or pi, which is 180 degrees, then this wedge becomes a stagnation flow type situation or a jet impingement. So, you have a plate now, the wedge has become a plate and the jet of air is impinging on it. The goal here is to understand whether this is a better situation, or when beta pi equal to 0, which is a flat plate configuration, which is going to give you a better heat transfer. So, a boundary layer develops like this. So, here's the situation where the wedge is now given an angle of beta pi equal to pi and m is equal to 1 in this case, and with that we can achieve what is called a stagnation point flow, as it is shown here in this picture. And this picture shows that there is some kind of flow coming in and it impinges, and this point is the so called stagnation point, and the flow, then this is the point of zero velocity at this point, and the flow then gets distributed depending on the jet, if it is a round jet or slot jet or whatever the jet the scenario may be, and it gets essentially flows out radially out in the case of circular jet. So, we look into some aspects of this and we will focus on the laminar boundary layer for now and not worry about turbulent boundary layer, but the discussions are equally good for laminar or turbulent boundary layer. So, we know for laminar boundary layer, the boundary layer thickness is given by this expression, and this delta is the velocity boundary layer or aerodynamic boundary layer divided by, if this is the x direction, is equal to 1 by square root of Reynolds number, local Reynolds number. Here u infinity is the free stream velocity that is entering the domain, and x is this direction, and this is the kinematic viscosity, that is dynamic viscosity by the density. So, if we replace this with some kind of, we replace u infinity with Rex and we get this, and we can find delta to have a function of such nature. What we are doing is that we are going to supply u infinity as very similar to the previous discussion, some kind of k, capital kappa type k times x as velocity, and x has units and k has units of 1 per second or 1 by s, units of 1 by s, and x is the local coordinate x. So, we can replace delta, and delta is equal becomes this expression, which is kinematic viscosity divided by k, this fellow. And moving forward, we can use that same expression and find the wall shear stress using the same the discussions you have had for wedge solution. We can obtain this for this case as well. Now, we can look at the situation for heat transfer. We can set notice that we can set m equal to 0, you will get a flat plate as I discussed previously, and m equal to 1. We can look at what will happen to the heat transfer. If you look at the Nusselt number, the local Nusselt number, when m is equal to 1 at Prandtl of 0.7 and divided by local Nusselt number at m equal to 0 and Prandtl number of 0.7, we find that the solution automatically gives you 1.7. This is the direct result of the wedge solution that was obtained, just plugging in values for m equal to 1 and beat up the wedge angle to 180 degrees and 0 degrees. With that, you get a solution immediately saying that an impinging flow is going to be 70% is going to give you 70% higher heat transfer coefficient compared to a flat plate case. That means this is your flat plate result, and so you are going to multiply by a factor of 1.7. So, it is very easy to see that a jet impingement is the better configuration, at least in the case of flat plate. When you impinge a jet, you get higher heat transfer coefficient compared to a flat plate. So, from this you can even get a expression for heat transfer coefficient in terms of the velocity kx. So, from this what we can come to a conclusion is that jet impingement is a better heat sinking configuration, albeit there is a minor increase in pressure drop compared to a flat plate. The pressure drop increase or the pumping power increase is slightly higher in the case of impinging jet compared to a flat plate. However, impinging jet is a very good configuration, flow configuration for heat transfer purposes or heat sink design purposes. So, moving forward, you can see here an example, some of the examples. This is a heat sink that is shown here. This is the flow inlet goes through this and exits on the other side of the page, and a processor is mounted, or the processor, this is the substrate, this piece is the substrate, these are pins that go into a socket, and this white color is the thermal interface material that bonds the heat sink to the package here. And these are some squares cut slotted heat sinks. These are the heat sinks that are typically used in power supplies in a desktop unit. This is a radially outflowing heat sink where the fan is mounted on the top and it pushes air down through this, and it apparently it is used in some of the processors. And here is another example of a fin. So, what we are going to look at is primarily focus on the parallel plate fin like that without any cuts or slots in between, but that can also be implemented easily, but we will not go into the details. So, what is the, how do we improve the heat sink performance? Typically the main challenges is that we talk about heat dissipation increases with surface area. We know that the flux increases with surface area, or heat dissipation. If my heat transfer coefficient is small or fixed or constant, then increasing the surface area gives me better or higher heat transfer rate or flux. Concomitantly, meaning that for the same situation, now you also have a lot more frictional pressure drop. So, you always see that the shear stress increases with increasing surface area. So, the goal is to understand the trade off, and that is what we did in the previous exercise of understanding heat transfer enhancement, is to balance or find the trade off between the two processes and come to a happy medium somewhere that provides the required heat transfer improvement. So, this is the typical stack that we have looked into. So, you have silicon die, there is a package substrate here, and the TIM integrated heat spreader, TIM heat sink. So, if you look at the thermal, so called thermal budget, is that you have, this is the silicon die, this is an example. You have a silicon die, this is the TIM material, then you have the heat spreader itself. So, this total accounts for this. This is actually a processor, someone who makes the processor controls this zone. So, nothing, as someone who develops heat sink solution, they cannot do anything to this, because this is part of the process development. On the other hand, one has access to this thermal interface material and also access to the heat sink solution. So, the heat sink solution in this case contributes to 42% of the total thermal resistance. This is Tj and this is your T ambient, and so this is your T case. So, you have a thermal resistance of T case, junction and ambient. So, the goal is to address only this part of the heat sink and see what is the quicker way of modeling these heat sink, obtaining some solutions, and we will go ahead and see those. And there is, when you try to understand these heat sink performance, and if we always see the enhancement, it is only a trial and error method that we discussed, is that we put some enhancement and see whether it works or not, and go back again, change the geometry, see if it works, go back. So, it is a trial and error, and there is no clear path that one can take or conceptual principle that one can take to achieving higher or better heat transfer or heat performing enhancement device. One has to go through that trial and error. So, one example where a principle can be used is a Reynolds analogy, but this Reynolds analogy has its own problems if one misunderstands it. These are the Reynolds analogy equations for a parallel, where you have advection term, this is the advection term that was discussed previously in the derivation, and this is the diffusion part of the equation. So, this equation holds true when the pressure gradient is almost 0. This is, for example, in anomalously is valid for a flat plate. It is an unusual case for flat plate that it happens to have the pressure gradient being small. So, in flat plate case, laminar flat plate case, you see that you get the clear term showing that okay, I have similar looking equations for momentum as well as for energy equation. So, with such a scenario, we tend to think that flat plate as an example of Reynolds analogy, but it is only a very exceptional case, but it is true for well mixed. Reynolds analogy holds true only for well mixed flows. And the reason we talk about Reynolds analogy is that what is the advantage of Reynolds analogy is that if you know the fluid part, then you can predict the heat transfer part. For example, in this case, equivalent boundary conditions if I use, then U star is equal to T star in these two equations. And then the partial derivative of U star with respect to Y star at wall and the temperature derivative, they become equal because they are similar in nature. So, with this concept, we can obtain an expression relating the skin friction, Reynolds number and the Nusselt number. So, what it does is that if I design a solution and if I find out its pressure drop, then I can automatically obtain the Nusselt number without even having to do any heat transfer experiment or measurement or numerical analysis. So once we know so that is the advantage of Reynolds analogy, because it's a hidden momentum transfer analogy. However, this, as I said, this holds true only for the well mixed flows. If I were to take the same expression and write it in terms of Stanton number, because the heat transfer enhancement adjudging technique that we discussed previously is based on Stanton number. So if I write the same expression in terms of Stanton number, you get Stanton number is equal to Nusselt by Reynolds divided by Prandtl. This denominator is nothing but Peclet number. With Prandtl equal to 1, the Reynolds analogy, which relates important parameters of the velocity and the thermal boundary layer, is this. So one makes a key assumption that Prandtl number is equal to 1, and this Prandtl number being equal to 1 is, you can see that it is only an exceptional case, anomalously valid for laminar flows in a flat plate. It never works out for other geometries of laminar flows. It's only working out only for the flat plate case. But if you are talking about a well mixed flow like a turbulent flow, the pressure gradient and the Prandtl number happens to be 1. The Reynolds analogy says that Prandtl number is equal to 1. That's it. That's the statement that Reynolds analogy makes. So with that, we obtain the condition. So Reynolds analogy is one such case when you are dealing with a well mixed flow conditions, then you may be able to extract Reynolds analogy to come up with a geometry that will give you better heat transfer or Nusselt number for a given or known pressure drop. So the extension of Reynolds analogy is the Chilton-Colburn analogy, but it has its own coefficient for Prandtl number, and this factor is called Cf by divided by 2 is equal to Stanton number times Prandtl raised to the power 2 by 3, and this is valid for this Prandtl number range. And as you can notice that it is not valid for Prandtl numbers. 0.6 is roughly the Prandtl number for all the gases, and this is called the J factor, the Colburn J factor. And again, this is applicable to turbulent flows without restrictions on dP by dx. In the flat plate case, it turns out that the pressure gradient happens to be negligible. Only in such situation this happens to be true. If the Prandtl number is more than 1, then you will end up having a difference, because you will end up having 1 divided by Peclet number here instead of 1 by Reynolds number. So that is why Prandtl number being 1 is a critical need for Reynolds analogies to exist. Okay. So beyond Reynolds analogy, we do not have any guiding principle in terms of understanding whether the geometry that you are selecting is going to work out or not, unless you have some information beyond just pressure drop. So that is the need, and so we need to go from a simple modeling exercise to understand how a given geometry is going to work out. So we will first look into the parallel plate heat sink. Here is the example of a parallel plate heat sink, where this is the so called heat sink base. These are your fins, and let us consider a fixed volume is available. Typically there is a volume is a fixed constraint. One has to fit a heat sink within a given volume, and in mostly in electronics there is not volume or space is premium, because we always target towards thinner and thinner devices, and thickness of the fin is to be treated as T sub f, and spacing between the fins, which is the channel width, is W sub c, and we are going to treat only the side inlet situation. And as you can see, when the flow enters, there is a contraction, that is, the flow enters from a larger channel and it has to contract to a smaller gap, because there is a fin here. These are fins, and the flow has to enter from a larger area into smaller area. So there is a separation that happens. So there is an entrance effect. Similarly, it has to expand from smaller area to larger area at the exit, and this is the exit. These are the exit effect. Exit effect, that is the expansion that happens at the edge. So that one has to account for K expansion, K exit, and this is about 10% of the heat sink pressure drop. So if you account for developing flow, that is X plus is the hydrodynamically developing flow, then one can obtain the contraction and the expansion coefficients as given here. WC is, as I said, spacing between the fins plus the thickness in the denominator. So this is a empirical relationship that was developed, and we use that, and so with that we can predict. This is the pressure drop part of it. So one can take this, and with the X plus and friction factor one can predict the pressure drop of this heat sink while accounting for the inlet and exit losses. So next part is to model the pressure drop, which is to say that the pressure drop is of the heat sink is nothing but core pressure drop, or what is happening between the fins as the flow enters and goes through the fin channel, and the other one is the inlet and exit losses. Now the core pressure drop is nothing but F apparent for the developing flows times the Reynolds number. This is the development length based Reynolds number, half rho v square. V is the velocity that is entering. The pressure loss at the inlet and exit are also taken into account, and friction factor for a parallel plate channel for a rectangular duct type channel is given by this expression in terms of development length. So using this empirical correlation, one will be able to predict the apparent friction factor, and from that apparent friction factor, once it's known, once the velocity is calculated, once the apparent friction factor is known, we substitute over here, and this is inlet and exit are purely geometric functions. So that with knowing the geometry, then we can predict this. Now we can predict the pressure loss, and as I said, this pressure loss tends to be approximately, if it is well designed, if it is not too dense a fin design, then it is about 10% of the total pressure drop, heat sink pressure drop. So that is the first order modeling one can account, but this is all empirical based. Let's go to the next, is to understand how to model a parallel plate heat sink from a first order perspective, just back of the envelope calculations. How do I calculate heat transfer or heat dissipation from this? Typically a heat sink resistance is employed, where we say T base minus T air inlet divided by the Q here stands for the heat transfer rate. In watts. So there are many models out there, and one of the model is so called convective resistance model, and in some textbooks you will see that convective resistance model is often employed to discuss fins, multiple fins in the conduction part of the chapter, where if you had more number of fins than a single fin, then we take the surface efficiency and calculate the heat transfer coefficient. But that model is what is shown here is T base minus T inlet by Q is equal to 1 by HA. HA is the surface enhancement or the surface efficiency, so which can be written as the prime plus the eta of the fin. Okay, this expression, as you can see, has its own, there is a bracket missing, has its own challenges. If the density, if I had a heat sink with closely placed fins, then this model fails, because it doesn't account for what the flow rate. It doesn't tell me how much flow rate is going through it. It doesn't matter to it in terms of whether the flow that is going between the fins is able to pick up the heat that was delivered from the fins. So instead, this model just says that it has a prediction that your heat transfer or resistance is going to be 1 by H, and in reality you never see such a relationship where RH keeps on increasing or the resistance of the heat sink keeps on decreasing as you increase the heat transfer coefficient. You see that at some point it actually asymptotes, and this asymptotic behavior cannot be captured here because of the wrong assumption that it happens especially for highly dense fins, that these 1 by HA does not hold. But if the fins are far apart and the separation between one fin and the other fin in the base of the heat sink is far apart, then you get this expression holds true, and we will discuss some aspects of it in the upcoming slides. So, the other model that is often used which recognizes the aspect that there is some flow going through these heat sinks into the page, for example. However, the flow, it has a certain amount of maximum temperature it can carry. It is the maximum temperature the flow can attain is the surface temperature of the heat sink itself. So, that some people capture it by just adding one more term called 1 by mCp. M is the mass flow rate, Cp is the specific heat. People turn Q equal to m dot Cp into delta T, which is inlet temperature. Delta T here is T out minus T in. But this is not a resistance. You cannot write this as a resistance because m dot Cp is not a resistance. This is an energy balance that we are employing. So, it gives a wrong impression as if this is a resistance. 1 by m dot Cp, if you write it as delta T by Q, which is a wrong, a thermodynamically wrong principle of resistance, because this is a consequence of heat being dumped into the flow stream. So, it just rises in temperature. It does not drive any heat transfer. A resistance is defined based on whether the maximum temperature and minimum temperature in the flow circuit, where heat is driven by the higher to lower temperature as flow goes through it. So, that is the point, and so this definition or this model is typically should be considered to be wrong. So, going back to the Nusselt number correlation, one can use LMTD or any other existing correlation and use that and combine it with the previous model that I just discussed here. And if it is a sparse fin heat sink, then one can use that and calculate the resistance for the heat transfer. With these two things, one can predict with as a first order business, we can calculate the pressure drop across the heat sink and resistance across the heat sink using empirical correlation. This is the first order model one can use to just size the initial heat sink, but this is based on empirism. So, can we do something that we can employ without empiricism is what we will try, or even have a model that works for any type of fin arrangement, meaning that whether it is densely packed fins or sparsely or spaced apart little larger. So, those type of fins, we will see how to approach that, and we will use the heat exchanger theory and to get to that point. These are some correlations that one can employ to understand the heat transfer coefficients. So, what we have done till now is that we discuss the heat sinks from a first order modeling perspective using the correlations and correlation for heat transfer and correlations for pressure drop or friction factor, using those how to model a parallel plate heat sink in a simplistic fashion. So, moving forward, we will try to these models have some limitations. Moving forward, we will try to change these models and see if we can use if we can get some physical insights into the problem and make use of heat exchanger theory, and that heat exchanger theory based model that can be applied to any kind of heat sink, not just parallel plates, for foam heat sinks and even array of ducts and so on, that we will discuss in the upcoming modules. So, the current model just is only valid for some sparsely phased fins. So, this gives us at least a back of envelope calculation to proceed in designing a heat sink based on longitudinal fin or parallel plate.